Today is March 14th, 2012, and this is Pi Day, and this is AP Stats.
You have to be recording this?
I forgot to record all that other stuff, but it's okay. We're gonna still hit the high. So it's on the recording. It's still, you got the benefit. The people who are absent,
Yeah.
they don't want to come to Pi Day.
You said screw that.
I did not.
Now the recording's got it.
All right.
We're just kidding.
Maybe they have family issues.
All right. So here we go. We're gonna finish. We're gonna take a look at this. Now we've got all that data in our calculator. We checked to find out whether it met the five conditions for doing inference with regression. We've got these numbers here to help us find the confidence interval. There's lots of numbers here. Not all of them are important. What are the numbers that are important for us to find the confidence interval for the slope? Where do we think the true slope is? For every extra fidget, how much weight loss do we think we achieve? Is probably the best way to answer this question. Without measuring everyone, we have a sample, and we get a slope. I'd really love to know what the slope is.
Coefficient
Of NEA change? I totally agree. So this negative 1.003 is our slope. Or for every additional calorie, you lose 0.003 kilograms. I think 0.003 kilograms is about the weight of 3 paper clips. But if you fidget a lot, that could be a lot of paper clips you lose. All right. So there we have it. We've got a B. We're also going to remember that the confidence interval formula follows the general form of a statistic.
Is that a fact that every calorie you lose that much more weight?
It's a very interesting question. Okay, what do we have here? We have sample data. For this group of people, this seems to be the relationship between energy expended and weight loss. The question that you're asking is it true? That question is exactly what this chapter is about. I have sample data. Do we think, in fact, there is a weight loss associated with fidgeting? For everyone. As if we did this with an entire population. Let's calculate the confidence interval for this slope and find out whether we can answer Jason's question. All right? Confidence intervals have the general formula of a statistic plus or minus a critical value multiplied by the standard deviation of the statistic. In our case, our confidence interval is found by taking the statistic, B, the slope that came from a sample, plus or minus the critical value. The distribution of B, when we don't know what the actual sigma, the standard deviation of that statistic is measured by T star. And the standard deviation of that statistic is measured by a quantity called the standard error of B. Where's the standard error of B on our Minitab output?
The coefficient constant, 3.505.
That is incorrect. The coefficient constant, this is the y-intercept. On your calculator, this is the number that would have come out of the A on the linear regression. Let me confirm that. Second, quit, second. Here's our linear regression. You see the 3.505?
Yeah.
It's the y-intercept. Okay? So, that number, 3.505, is not.
Any change in standard
Okay.
error.
Okay, so Paul, you're seeing where this heading that says standard error, and then down here, there's our standard error, 0.0007. All right? That's our standard error of B. Hi, Paula. What can I do for you?
Good morning. Thank you.
Hold on. Yeah, I got it.
Okay. Thank you.
Yeah. Oh, I think I have him. His name? Oh, yeah, there. Sorry, I thought you were Nicole. And just going back to the old joke, just a joke, just like my whole class is a freaking joke. All right, so here we go. Calculate by hand the confidence interval. Confidence interval equals B 0.00344415 plus or minus a T star value. Get out your probability. Can I extend a personal invitation for you to get your stuff out? Your probability tables that allow us to actually do this work. Probability tables. Okay, so I need, once you get your probability tables out, a T star value associated with 90% confidence interval, and I don't know how many degrees of freedom we have in this case. I do, but I'm pretending not to know. 14 because there are 16 data items. 16 minus 2. What? It says down here. Construct and interpret the 90%. All right, so what do you got for me? 90%, 16 degrees of freedom. 1.746. And then I'm going to multiply this by the standard error 007414. 7.41. Wait, 1.7. Okay, let's try this one again. 90% confidence, 14 degrees of freedom.
Okay, sorry.
1.7.
You've been outvoted. Let's here. Okay. 761. You're at 60. You're at 16 degrees of freedom.
No, I said 17.
Well, I think that's the
All right. So there's our formula. I'm still trying to answer Jason's question. Is this real? Is this true? Well, let me put these numbers in. Negative 0.0034415 minus 1.761 times 0.0007. Okay, so there's our bottom end of our confidence interval. Come back. Where's my calculator? View, always in front. There we go. So the low end of that confidence interval is negative 0.004747. What about the upper end? Is there some way that I can do this without typing in all those numbers again? Second, enter, will get me back what I just entered. By the way, second, go to the left, will take me all the way back to the beginning so I don't have to go through all those numbers. Thank you. I think that was a compliment. Oh, okay. And then the upper end of that interval is negative 0.002136. All right. Now, why and how does this help me answer the question that Jason asked? Is this true? Is it really that you fidget? If you fidget, you lose weight? Well, let's go through the mantra of what that confidence interval says. With 90% confidence, we believe that the true slope of weight loss versus fidgeting, meaning if I did it for the entire population, is somewhere between negative 0.004 and negative 0.002. Let me say that again with emphasis on different words. 90% confidence, I believe the true slope is between negative 0.004, is between negative 0.004 and negative 0.002. So no matter what I think the true slope is negative. Which means no matter what I think the true slope is, when you fidget more, for every bit of fidgeting, you lose weight. That's the power of this inference procedure. We looked at a sample, but we think we're at least 90% confident that this would be true at the population
So
level.
what is fidgeting?
I have no idea.
Like there's
That's
different
just-
types.
That's
There's
just
different
moving,
types of fidgeting.
like sitting and doing this pretty
I'm
much.
gonna start doing that.
Jason, you do not have a problem with weight.
I don't, you're right.
I should fidget.
No, I'm sure you should.
I got the 40-year-old punch.
I'm trying to get a six pack. I had one back in middle school.
Jason, if we start believing that your glory days, the best days of your life were in middle school, oh my gosh, I'm so sorry for you. Okay. Oh, actually, the flat. In ninth grade, I didn't go to middle school. I went to junior high, and in my ninth grade, junior high, the last day I was voted most likely to succeed. So maybe ninth grade was my glory days. Maybe I did peak at ninth grade.
That's when you had that
Tell you.
whole luscious locks.
Yeah, I had hair then. Okay. By the way, I took you through this procedure because, of course, we can write assessment questions that force you to be able to look up the T star value, to be able to know where you're going to find that standard error of B value, that kind of thing. But of course, anything that's hard to do from this procedural standpoint can probably be done automatically on the calculator. Let's see if we can find out where on the calculator we can find the confidence interval for B without actually doing all the grinding work. This is where you guys think, where do we find inferential statistics stuff on the calculator? Stat, great choice. Test, another great choice.
Either F or G.
Well, let's take a look at the bottom. What we just did was an interval, right?
So I'm going to go with G.
G, lin reg, linear regression, T interval. Did we use a T statistic?
Yeah.
Sure did. All right, so let's take a look at option G, the lin reg interval.
90%
Okay, X-less, Y-less. Oh, we already have that data in. Good. Frequency, 1. Good. Confidence level, 90%. Great. I'm not going to put anything in linear regression.
This is 95.
Oh, 95. I'm sorry. 0.9. All right. And then I'm going to leave the regression equation blank because we're using the one that just comes out from the natural data. We can actually do some forcing of things, but we're not going to do that on this problem. And hopefully we get the same numbers out that we got before. Up between negative 0.004 and negative 0.002. That looks like about what we said, right?
Yeah.
Excellent. All right, so got to be able to grind out the answer by hand because, of course, you know there's going to be some multiple choice question that's going to force you to know what the formulas look like by hand. But in general, what's going to really happen? You're going to use the calculator, or people use the software to find out what those confidence intervals are. All right. Let's go back to the slideshow. I can't find the slideshow. There we go. Oh, because this is on top. There we go. So Hear them going through, let's see if we hit all the high points. Did we check it? Did we check to see if it was linear?
Yeah, man, we did all
Yeah, we did all of that. Well, we didn't do the histogram. We did something better.
We did that.
Normal probability plot. So we set aside the linear equation. Do we think there's more than 160 fidgety people? Oh yeah. Do we look for the histogram? We looked at the normal probability plot. No obviously departures from normality. Did we say equal variance? We looked at the residual plot for equal variance, and we're good there too. And random, the people were selected randomly, so we're good on the unbiased part too. All right? And there's their calculation.
Looks like ours.
Looks like ours. Looks like we did a great job, including finding the proper T star value.
And the proper equal variance.
See, Paul uses his right hand to pat himself on the back on the left-hand side, then he uses his left hand to pat himself on the back on the
I
right-hand
always
side.
use my hands.
All right.
It was here.
Okay. All right. And then the last thing, and of course, the interpretation is the most important. With 90% confidence, we think that the true slope is between negative 0.004 and negative 0.002. And the most important part of that is that interval doesn't include 0. All those numbers are negative. Whatever the true slope is, we're pretty confident that's a negative number and that fidgeting does lead to weight loss. All right. Now, that's the confidence interval version of this. But we know for every inference procedure that we've done so far, except for the chi-squares, whenever we had a confidence interval over here we had a thing called the significance test. Let's take a look at what the significance test looks like for inference, and then we're going to be all done. All right? First of all, we need to talk about what our test statistic is going to be. In the confidence interval problem, we use T star. In the inference test, we're going to use just plain old T. The value of T is going to be calculated by taking B, the sample slope, the slope that we got from the data from our data taking, and we're going to subtract it by beta naught. Beta naught. Where could beta naught be coming from? No, I don't want. With every significance test that we've done, we started with an H naught and an HA claim. A claim about what the true slope may be. Now, Jason may want to ask the question, does fidgeting really help you lose weight? The answer to that question he would like to be is, yes, it does help you lose weight. He would like to show that beta is less than 0, that beta is negative, that the slope is negative. For every 1 more calorie of fidgeting, you have a loss in weight. That's what he'd like to prove, to find out the answer to that question. Is this true? If beta is less than 0, if beta negative is our HA claim, what do you think our H naught claim is going to be?
Equals 0.
Because you've seen this movie before, haven't you, Kyle? Whatever shows up here, the equal version shows up there. That's exactly right. So this is just like those inference tests that we've done before. So what could happen here? Well, the HA claim could actually have 3 different variations, couldn't it? Beta not or less than 0, beta not equal to 0, beta greater than 0. But the HA claim is always beta equals something. All right? So, as we look at your scaffolding sheet for inference, you're going to see, again, in step 1, HA and H naught. Beta equals versus beta some form of not equals. All right? Let me get rid of my writing. All right? So, the t-test for the slope of least squares regression line, T is equal to B minus beta naught over SE of the standard error of B. And we have three different versions of the alternate hypothesis. If our alternate hypothesis is beta greater than something, we're going to be looking at upper tail test. If it's beta less than something, we're going to be looking at the lower tail test. And if it's beta is not equal to, we've got the two-tailed test. Again, just like we've done with other Z and T tests. Hey, let's figure out the T statistic. Let's figure out the T statistic for this problem that we just did. In this case, what was B? What was the B that came out of our calculator? I have to go back a little ways. There it is. What was our B? Negative 0.003. Okay, let's use that value. Negative 0.003. What was our beta naught? What was the beta value associated with the null hypothesis? 0. And then what was standard error of B? That number was only in that Minitab output. What was that? It was not negative. Standard errors can't be negative. But I think you're right. It was like negative. It was 0.007. Let's go back. It's right there. Negative. Oh, it's 0.0007414. 0.0007414. Right? Let's go ahead. Let's calculate that. Negative 0.003. I'm not going to do minus 0 because it won't make a difference. Divided by 0.0007414. And I get a t value of negative 404.6. I wonder what we do with that value. I don't know. What did we do in earlier significance tests once we got a test statistic? We got to go to the chart. We got to convert it into a. Starts with a probability. What's the p-value associated with that test statistic? What is the probability that our t-value, and we need a less than or greater than sign here.
Greater than, less than, equal to. Less than.
Equal to, less than, greater than.
Okay, we never put an equal sign there, ever, have never done it. So it's not an equal to. The question was, what was the alternate hypothesis? Beta less than 0. So we always put the same direction in there. What's the probability that our t-value is less than negative 4046? Now the t-values on your probability table are all positive, so we're actually going to convert that to what's the probability of t being greater than 404? And remember that we are stuck with 14 degrees of freedom. So go to your 14 degrees of freedom line, look up that 404, and you say it falls between
0.0005.
Okay. While we're at it, though, I got to show you where the I got to do one more thing on the calculator, and then we're going to do the craziest example in the book. All right. I want to do that. I want to get that p-value out of our calculator without doing all the hard work. And again, I want you to step up here. I want you to say, what do you think I have to look to find out find the p-value associated with that?
Stat test.
Stats, tests.
Go to the bottom.
Let's do F, the Lin-Reg t-test. Okay. Now,
I've never seen that.
that's because the first time we've ever been here. All right. Now, here's where I'm a little angry at Texas Instruments. Just a little bit. What? All right. So here's the page. Here's the page of things that we have to do in order to do a. Actually, I haven't looked at this version on whether they corrected the error that I'm going to point out to you on the Inspire or not. Right? The Lin-Reg t-test says, okay, tell me where your data is. Okay, it's an L1 and L2. That's where we put it. That works pretty good. Okay? And then down here, on that line, beta and rho not equal to 0. Or beta and rho less than 0. Or beta and rho greater than 0. Let me interpret what's going on here. For the Texas Instrument calculator, there is only one null hypothesis that can be done on the calculator. And that is beta equals 0. All you can adjust is which version of the alternate hypothesis you use based on 0 being the slope. So, this calculator, for that particular problem, can answer the question, do we think we have a negative slope here? Do we think fidgeting leads to weight loss? But for other questions in which maybe we ask the question, hey, is beta equal 1? Our calculator can't help us. We have to use the T formula that we talked about just a little bit earlier. This page assumes, nope, I guess I can't write on that. This page assumes H0 is beta equals 0. Well, let's go ahead and at least have it do our problem. We want to have our alternate hypothesis as beta is less than 0. We can have it calculate it. And Katya, you said the p-value is between 0.0005 and 0.001. Do we have a consistent thing there? That would be what? 0.00019. Yep, right in that range. And for you guys, what does that mean? Oh, the p-value is really low. Low p-values lead you to reject H0. High p-values is a fail to reject. So we say, because the p-value is lower than our alpha value of 0.05, we reject H0. Context statement. There's sufficient evidence to suggest that the HA claim is true, or that for every additional bit of fidgeting, you get some weight loss. All right, so here we go. We're going to finish up with one last example. I'm just going to read it to you straight. Infants who cry easily may be more stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between crying of infants 4 to 10 days old with their later IQ scores. A snap of a rubber band on the sole of the foot caused the infants to cry. Researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ at age 3 years using the Stanford-Binet IQ test. The scatter plot and mini-tab output are shown.
Is this even legal?
What, you don't think it's legal to take a rubber band and slap it onto a baby's foot?
Shouldn't you not do that?
Should you not do that? I think it's pretty bad. But they didn't ask me. Okay, so here's the idea. So at 4 days old, can we snap a rubber band and figure out how smart the kid's going to be? That's what this question's asking. Is there a relationship between the intensity of crime and their measurable IQ later? Yeah, every time I do this example, I'm like, you've got to be kidding me. So they have these kids, these doctors, torturing the kids. Okay, now, something I didn't point out earlier, but I'm going to point out now. I'm going to circle the important numbers from the mini-tab output.
S is pretty important.
Well, S is used to find,
How much it varies from the slope on every.
right,
on every-
but in our day-to-day calculation stuff, it's not as important. You know that the coefficients determine the line of best fit. The slope is 1.49. Oh, which means for every additional peak of crime, it's like you gain 1.5 points in IQ. That's what the interpretation of that slope is. Okay? We have the SE coefficient that would be used to calculate the t-value. But the last thing I circled is the t-value, assuming an H0 claim of 0. So the mini-tab output can actually calculate the t-value for you. So the question is, do we think crying is a predictor of IQ? There were, how many kids in this? 38 infants in this study. 38 infants, how many degrees of freedom? 36 degrees of freedom. Can you do a quick lookup on the T-chart of 36 degrees of freedom? What's that? Oh, that P. Oh, is that P there?
Bring it out,
If you look up, if you look up, the quiz is tomorrow.